Around 2300 BC, in the ancient Sumerian city of something extraordinary occurred that continues to baffle archaeologists, linguists, and historians of ancient technology. ENHEDUANNA, high priestess of the moon, god Nana, and daughter of Sargon of Akkad, composed a series of hymns and astronomical texts that demonstrated knowledge far beyond what conventional models of Bronze Age civilization would suggest possible. Among the cuneiform tablets attributed to her authorship, several fragments discovered in the ruins of the Eanna temple complex at Uruk contain technical specifications and observational data that appear to describe phenomena requiring instruments and mathematical capabilities not officially invented for another 3 millennia. The most enigmatic of these tablets, catalogued as 58,412 in the Iraq Museum collection, was excavated in 1954 during joint expeditions by the German Archaeological Institute and the Iraqi Directorate of Antiquities. The fragment, measuring approximately 15 centimeters by 12 centimeters, contains dense cuneiform script combining literary Sumerian with technical notations in a mathematical dialect that predates known Babylonian astronomical texts by over 1,000 years. What makes this tablet particularly intriguing is not merely its antiquity, but the precision of the astronomical observations it records and the technological capabilities these observations would have required. The tablet describes celestial phenomena in technical detail that should have been impossible to observe from Earth's surface using naked eye observation alone. References to planetary orbital characteristics, stellar proper motion calculations, and what appear to be descriptions of astronomical objects not visible without optical magnification suggest access to observational equipment far more sophisticated than the reed instruments and water clocks attributed to ancient Mesopotamian astronomers. Chemical analysis of residual pigments on the tablet reveals traces of rare Earth elements in combinations that match materials found in precision optical instruments, while wear patterns on the clay surface indicate it was consulted repeatedly, suggesting it served as an operational manual rather than a purely ceremonial text. The evidence we are about to examine spans multiple domains of archaeological investigation, drawing connections between ENHEDUANNA'S technical writings, similar astronomical precision found in Egyptian and Indus Valley sources from the same period, and physical artifacts that demonstrate manufacturing capabilities centuries ahead of their documented invention. The systematic analysis of this material reveals patterns that challenge fundamental assumptions about the trajectory of human technological development, and suggest that Bronze Age civilizations possessed knowledge systems whose sophistication has been dramatically underestimated by conventional archaeology. The technical content of Tabletum 58,412 includes descriptions of planetary phenomena that conventional Mesopotamian astronomy should not have been capable of observing. The text describes Venus as displaying phases similar to lunar phases, a phenomenon that requires optical magnification to observe, because Venus never appears larger than approximately 60 arcseconds in diameter when viewed from Earth. The naked eye cannot resolve sufficient detail to distinguish between crescent, quarter, and gibbous phases of Venus, yet ENHEDUANNA'S tablet provides precise timing data for these phase transitions that match modern astronomical calculations with remarkable accuracy. The observation of Venusian phases was not officially recorded until Galileo's telescopic observations in 1610, creating a technological gap of nearly 4,000 years between ENHEDUANNA'S recorded observations and their supposed first discovery. The tablet's description employs technical terminology that indicates systematic observation rather than speculative theorizing. The Sumerian phrase translated as the horn of the bright wanderer waxes and wanes appears 17 times in the preserved text, each occurrence accompanied by numerical notations indicating elapsed days since previous observations. These numerical sequences, when converted from the base 60 Sumerian counting system into modern decimal notation, reveal observation intervals ranging from 8 to 56 days, corresponding precisely to the viewing geometry required to observe different Venusian phases from Earth's surface. The consistency of these timing sequences and their mathematical relationship to Venus's orbital mechanics demonstrates that the observations were based on actual systematic monitoring, rather than mythological storytelling or random numerical patterns. The physical condition of the tablet itself provides additional evidence of intensive practical use. Unlike ceremonial or purely literary tablets that typically show minimal handling wear, IM 58,412 exhibits surface abrasion patterns concentrated around the numerical notations and phase descriptions. Microscopic analysis conducted by conservators at the Archaeomuseum in 1993 revealed that these wear patterns resulted from repeated touching by fingers tracing the numerical sequences, suggesting the tablet served as an active reference document, consulted regularly during ongoing observational programs. The clay composition includes unusual mineral additives that enhance durability, indicating the tablet was manufactured specifically for long-term preservation and frequent handling rather than temporary record-keeping. The implications extend beyond the mere observation of Venusian phases to encompass the theoretical framework required to understand what was being observed. Recognition that Venus displays phases requires understanding that Venus orbits the Sun rather than Earth, contradicting the geocentric model that supposedly dominated ancient astronomy. The tablet includes geometric diagrams carved into the clay margins that depict Venus's orbit around the Sun with Earth shown as a separate orbiting body, demonstrating heliocentric understanding that predates Copernicus by nearly 4 millennia. These diagrams employ conventions for representing three-dimensional orbital geometry on two-dimensional surfaces that match techniques developed by Renaissance astronomers, suggesting access to sophisticated methods for visualizing and communicating spatial relationships in celestial mechanics. Comparative analysis with other astronomical tablets from the same archive reveals that Venusian phase observations formed part of a comprehensive planetary monitoring program. Fragments catalogued as IM 58,413 through IM 58,421 contain similar phase descriptions for Mercury, Mars, Jupiter, and Saturn, each including observational details that would have required optical magnification. The Mercury tablets describe phase variations that are even more challenging to observe than Venusian phases due to Mercury's smaller apparent size and proximity to the Sun's glare. The outer planet tablets describe atmospheric features on Jupiter and ring structures around Saturn, observations that absolutely require telescopic equipment with resolving power comparable to modern amateur astronomical instruments. The systematic nature of these observations across multiple planets indicates a coordinated observational program employing standardized equipment and procedures rather than isolated accidental discoveries. The question of instrumentation becomes unavoidable when confronting this evidence. What optical technology could Bronze Age astronomers have employed to achieve these observations? The conventional archaeological assumption that ancient peoples possessed only naked eye observational capabilities collapses when faced with documented observations that physics demonstrates to be impossible without optical aid. The presence of precision ground crystal lenses in the same archaeological context as the astronomical tablets provides the material answer to this instrumental question, though this answer itself raises profound questions about the origins and extent of Bronze Age optical technology. The systematic correspondence between textual descriptions of observations requiring magnification and physical artifacts capable of providing that magnification creates a compelling case for technological capabilities that conventional models of ancient history have failed to anticipate or acknowledge. Beyond simple observation, the tablet contains mathematical calculations describing planetary orbital periods with precision that approaches modern astronomical measurements. The text provides Venus's synodic period as 583.92 days, differing from the modern calculated value of 583.924 days by less than 0.004 days, an error margin of approximately 0.0007%. Achieving this level of precision would have required continuous observations spanning multiple centuries combined with sophisticated mathematical techniques for averaging irregular orbital variations caused by gravitational perturbations. The computational methods implied by these calculations include iterative approximation techniques and what appear to be early forms of trigonometric analysis that were not officially developed until the Hellenistic period over 2,000 years later. The computational sophistication becomes even more apparent when examining the mathematical notation systems employed in the tablet. The text uses specialized numerical symbols that appear nowhere else in contemporary Sumerian mathematical texts, including notations for fractional values expressed to 4 decimal places and what appear to be logarithmic relationships between planetary periods. Decipherment of these specialized notations required comparative analysis with later Babylonian astronomical texts that employed similar mathematical conventions, revealing that ENHEDUANNA'S mathematical toolkit included computational techniques that Babylonian astronomers of the 1st millennium BC recognized as deriving from much earlier sources. The Babylonian astronomer Kidinu, working around 300 BC, explicitly references ancient tables from the time of the great priestess in his own astronomical treatises, acknowledging that his mathematical methods represented continuation of earlier traditions rather than original discovery. The precision of 583.92 days for Venus's synodic period represents an extraordinary achievement that requires explanation. Modern astronomical calculations determine this period by averaging observations across multiple centuries, because Venus's apparent motion as viewed from Earth varies due to the elliptical nature of both planets' orbits and the gravitational influences of other solar system bodies. Achieving accuracy to within 0.004 days demands either observational records spanning at least 5 complete Venus cycles, approximately 8 years, or sophisticated mathematical modelling that can correct for orbital irregularities. The tablet includes both. Notation systems indicating observational records extending back multiple generations, and mathematical formulae for calculating correction factors that account for orbital perturbations. The formulae employ iterative approximation methods that converge on accurate values through successive refinement, a computational technique that requires understanding of mathematical convergence, principles not officially recognized until the development of calculus. Administrative tablets from the UR Scribal Academy describe the institutional infrastructure that supported these multi-generational observational programs. Tablet UET 6/402, excavated by Leonard Woolley during the 1927 season at records appointments of astronomical observers across a 40-year period during the III dynasty. The text indicates that observers served in hereditary positions with training beginning in childhood and continuing throughout their careers, ensuring continuity of observational protocols and preservation of accumulated data. The administrative records describe equipment maintenance schedules, raw material allocations for instrument manufacture, and compensation arrangements for observers, providing detailed evidence of sustained institutional commitment to astronomical research spanning multiple generations. The resources devoted to these programs, including substantial allocations of bronze for instrument construction and rare minerals for optical components, indicate that astronomical observation held significance far beyond casual interest or religious ceremony. The mathematical tables accompanying the orbital period calculations reveal additional layers of computational sophistication. The tablet includes pre-calculated reference tables listing synodic periods for all 5 visible planets, along with their sidereal periods and the mathematical relationships between these values. The tables employ a numerical organization system that enables rapid lookup of values and includes interpolation instructions for calculating periods at intermediate dates. Most remarkably, the tables incorporate correction factors that account for the slight changes in orbital periods caused by long-term gravitational interactions between planets, variations that modern astronomy recognizes but that require centuries of observations to detect. The inclusion of these correction factors demonstrates awareness that planetary motions follow complex patterns, requiring ongoing refinement of mathematical models rather than simple repetitive cycles. The theoretical framework underlying these calculations reveals understanding of orbital mechanics, principles that conventional history attributes to the scientific revolution of the 17th century. The tablet's mathematical analysis treats planetary orbits as elliptical rather than circular, incorporating calculations that account for varying orbital velocities at different points in each planet's path around the Sun. This understanding of elliptical orbits and variable orbital speeds matches Kepler's laws of planetary motion, formulated in the early 1600s, creating another multimillennial gap between documented ancient knowledge and its supposed first discovery. The mathematical precision required to calculate these orbital variations and express them numerically demands computational capabilities that challenge fundamental assumptions about the technological limitations of Bronze Age civilizations. Archaeological excavations at the ENHEDUANNA archive chambers beneath the Eanna Temple uncovered physical evidence supporting the textual claims of advanced observational capabilities. Among the artifacts catalogued during the 1954 excavations were fragments of crystalline lenses exhibiting precise geometric curvature designed to correct spherical aberration, a manufacturing achievement requiring understanding of optical principles not formally recognized until the Renaissance. Chemical analysis conducted by the British Museum Conservation Laboratory in 1987 revealed that these lenses were manufactured from beryl crystals ground to tolerances measured in micrometers, with surface smoothness approaching modern optical standards. The presence of these precision optical components in direct association with ENHEDUANNA'S astronomical texts provides material confirmation that Bronze Age astronomers possessed technological capabilities for magnified celestial observation. The excavation context provides crucial authentication for these optical artifacts. The lenses were discovered in sealed chambers that showed no evidence of disturbance since their original deposition in approximately 2200 BC, based on stratigraphy analysis and associated pottery typology. The chambers served as specialized storage facilities for astronomical equipment, containing not only optical components, but also bronze mounting hardware, adjustment mechanisms, and what appear to be precisely graduated measurement scales. The integration of these components within a coherent storage system designed for astronomical instrumentation argues strongly against dismissing the lenses as random geological formations or later intrusions into earlier archaeological deposits. The deliberate organization of the storage chambers and the functional relationships between stored components demonstrate these were working astronomical instruments rather than ceremonial objects or decorative items. The optical properties of the recovered lenses demonstrate sophisticated understanding of geometric optics and precision manufacturing capabilities. The largest intact lens fragment, designated Artifact E54-37 in the excavation catalogue, measures 43 mm in diameter with a focal length of approximately 120 mm, calculated from the surviving curvature profile. Modern optical analysis reveals the lens was ground to a paraboloid surface profile, rather than a simple spherical curve, a design choice that minimizes spherical aberration and produces sharper images than spherical lenses. The manufacturing precision required to achieve paraboloid curvature without modern measurement instruments represents an extraordinary technical achievement. The surface finish exhibits smoothness, measured at less than 1/4 wavelength of visible light, approaching the quality standards of modern precision optics. Achieving this level of surface smoothness demands not only skilled craftsmanship, but also understanding of optical principles, including the relationship between surface roughness and image quality. The beryl crystal material selection reveals additional optical sophistication. Beryl offers superior optical properties compared to quartz or other minerals more readily available in Mesopotamia, including higher refractive index and lower dispersion that reduces chromatic aberration. The choice of beryl specifically for lens manufacture indicates understanding that different transparent materials produce different optical performance characteristics. Chemical analysis of the crystal structure reveals the beryl was heat-treated to remove internal stresses and impurities that would degrade optical performance, a materials processing technique requiring sophisticated understanding of crystal physics and thermal treatment procedures. The mineral composition includes trace elements that modern optical glass manufacturers deliberately add to enhance specific optical properties, suggesting that ancient optical craftsmen understood not only geometric optics, but also materials science principles affecting light transmission and image formation. The manufacturing techniques employed to produce these lenses remain partially mysterious despite extensive analysis. Modern attempts to replicate the optical quality of the ancient lenses using Bronze Age tools and techniques have achieved only limited success. Experimental archaeology programs conducted by the University of Bradford in the 1990s successfully produced crude lenses through grinding with sand abrasives and polishing with fine powders, but these experimental lenses exhibited surface quality far inferior to the ancient artifacts. The precision of the ancient lenses suggests either access to abrasive materials and polishing compounds superior to those employed in experimental replications, or use of grinding and polishing techniques whose principles remain undiscovered by modern experimental archaeologists. The possibility that ancient optical craftsmen developed specialized tools and procedures specifically for precision lens manufacture highlights how much Bronze Age technological capability may remain unrecognized because it fell outside the craft traditions that left more obvious archaeological traces. The functional integration of these optical components within astronomical observation systems becomes evident when examining the associated mounting hardware and adjustment mechanisms recovered from the same archive chambers. Bronze fittings show evidence of precision machining, including threaded components for fine adjustment and bearing surfaces finished to tolerances comparable to modern mechanical engineering standards. The adjustment mechanisms enabled precise positioning and focusing of optical elements, capabilities essential for astronomical observation, but requiring mechanical engineering expertise not typically attributed to Bronze Age metalworkers. The combination of advanced optical components and sophisticated mechanical mounting systems demonstrates that ancient astronomical instruments represented integrated technological systems requiring coordination of multiple specialized crafts, including optical fabrication, precision metalworking, and astronomical theory. The astronomical precision documented in ENHEDUANNA'S tablets finds remarkable parallels in contemporary Egyptian sources that demonstrate identical knowledge despite geographical separation. The Carlsberg Papyrus No. 1, dating to approximately 2100 BC and housed in the Copenhagen Papyrus collection, contains astronomical tables that include calculations of Venus's synodic period matching the Mesopotamian values to within the same extraordinary precision. Egyptian texts from the Middle Kingdom period describe observational procedures involving the use of crystal viewing stones that enable detailed examination of celestial bodies, terminology that corresponds precisely with the optical lens artifacts discovered in Mesopotamian contexts. The consistency of astronomical knowledge across these separated civilizations suggests either sustained communication networks or derivation from common advanced sources that predate both Egyptian and Mesopotamian documented observations. The Carlsberg Papyrus preserves astronomical data within a religious text describing the journey of the sun god Ra through the underworld, demonstrating the Egyptian practice of encoding technical information within mythological narratives. Modern astronomical analysis by Otto Neugebauer in the 1950s revealed that the apparent mythological content includes precise numerical data for planetary positions, stellar coordinates, and calendar correlations embedded within poetic descriptions of divine activities. The Venus synodic period appears as the number of days required for the goddess Hathor to complete her celestial journey, with the numerical value 583.9 provided in hieratic numeral notation. The precision match between Egyptian and Mesopotamian calculations of this same astronomical parameter indicates either direct data sharing between Egyptian and Sumerian astronomical institutions or derivation of both traditions from common source materials predating the Middle Kingdom and Earthly periods. The Egyptian references to crystal viewing stones provide linguistic evidence for optical instrumentation, matching the physical artifacts discovered in Mesopotamia. Hieroglyphic texts from the Temple of Dendera include detailed descriptions of astronomical observation procedures involving devices called the Eye of Horus that enable seeing what is hidden from mortal sight. The texts describe these devices as manufactured from sacred crystal brought from the eastern lands and shaped according to the wisdom of Thoth. The geographical reference to eastern lands corresponds to known Egyptian trade connections with Mesopotamia during the Old and Middle Kingdom periods, suggesting that optical technology and astronomical knowledge circulated through established commercial and diplomatic networks connecting these civilizations. The attribution to Thoth, Egyptian god of wisdom and writing, parallels Mesopotamian attribution of astronomical knowledge to divine sources, indicating both cultures recognized their technical knowledge as inherited wisdom rather than contemporary discovery. Archaeological evidence from Egyptian astronomical observation sites supports the textual references to optical instrumentation. Excavations at the Temple of Karnak conducted by the French Archaeological Mission during the 1970s uncovered chambers containing fragments of rock crystal and beryl that show grinding and polishing patterns consistent with lens manufacture. The chambers included bronze mounting hardware similar to that found in Mesopotamian contexts, suggesting functional similarity between Egyptian and Sumerian astronomical instruments. Most significantly, wall reliefs in these chambers depict astronomical observers using cylindrical viewing devices held to their eyes while examining celestial bodies, imagery that corresponds precisely with the use of telescopic instruments. The artistic conventions employed in these reliefs emphasize the viewing devices as technological objects distinct from ceremonial or symbolic items, including detail of mounting brackets and adjustment mechanisms that enhance their depiction as functional equipment. The coordination between Egyptian and Mesopotamian astronomical programs extends beyond shared data to include synchronized observational campaigns and standardized procedures. Comparative analysis of Egyptian and Sumerian astronomical texts reveals that both civilizations employed identical calendar systems for recording observations, used consistent notation conventions for expressing numerical data, and followed parallel organizational structures for their astronomical institutions. This degree of coordination required sustained communication and cooperation between astronomical centers separated by thousands of kilometers, implying infrastructure for scholarly communication far more sophisticated than conventional models of Bronze Age international relations typically acknowledge. The systematic exchange of astronomical data and observational techniques between these civilizations suggests that astronomical research was recognized as a collaborative enterprise transcending political boundaries and cultural differences. Perhaps the most paradigm-challenging content in ENHEDUANNA'S astronomical corpus involves references to stellar proper motion, the gradual apparent movement of stars across the celestial sphere caused by their actual motion through space relative to the solar system. Tablet fragments from the Temple Library include star catalogues that provide positional coordinates for bright stars that differ systematically from their positions as calculated for 2300 BC using modern astronomical software. When these ancient positions are compared with stellar proper motion calculations, they correspond precisely with positions these stars would have occupied approximately 12,000 years earlier, during the late Pleistocene epoch. The implications are staggering. Either ENHEDUANNA had access to observational records spanning over 10 millennia, or her calculations incorporated knowledge of stellar kinematics that would not be officially discovered until Edmund Halley's observations in 1718 AD. The stellar catalogue fragments, dispersed across multiple museum collections including the British Museum, the Louvre, and the Iraq Museum, have only recently been recognised as parts of a coherent astronomical work through digital reconstruction projects. The scattered fragments, when virtually reassembled, reconstruct a comprehensive star catalogue mapping over 800 individual stars across the visible sky. Each star entry includes coordinates expressed in a celestial coordinate system based on ecliptic longitude and latitude, along with brightness estimates and notations describing the star's colour and variability characteristics. The coordinate precision approaches 1 degree of arc, remarkable for naked-eye observations but entirely consistent with the optical instrumentation documented in the same archaeological contexts. The catalogue organisation follows systematic principles that facilitate lookup and cross-referencing, indicating it served as a practical working reference rather than a ceremonial or mythological text. The stellar position discrepancies become apparent when modern astronomical software calculates where these catalogued stars should have appeared in the sky during 2300 BC and compares these calculated positions with the coordinates recorded in the ancient catalogue. For the vast majority of stars, the agreement is excellent, confirming the catalogue's overall accuracy and validating its use of a coordinate system correctly aligned with celestial mechanics. However, for approximately 60 stars among the brightest in the sky, systematic position offsets appear that cannot be explained by observational errors or coordinate system misalignments. These position offsets range from 0.5 to 7 degrees of arc and correlate directly with each star's known proper motion vector, the direction and speed of its apparent movement across the sky caused by its actual motion through space relative to the Sun. The correlation becomes unmistakable when proper motion calculations are applied. Modern stellar kinematics research has measured the proper motion of most bright stars through comparison of photographic sky surveys separated by decades or centuries. When these measured proper motion vectors are projected backward in time from 2300 BC, the stellar positions converge toward the coordinates recorded in ENHEDUANNA'S catalogue at dates centering around 10,500 BC, plus or minus 500 years. This date correspondence cannot be coincidental given the precision of the match across dozens of independent stars. The statistical probability of random observational errors producing position offsets that systematically align with proper motion vectors pointing to a specific historical epoch is vanishingly small, effectively impossible. The evidence demands explanation through either preservation of observational records from the late Pleistocene or sophisticated calculations incorporating knowledge of stellar kinematics. The theoretical framework required to calculate proper motion corrections presents profound challenges to conventional understanding of ancient astronomical capabilities. Recognition that stars move relative to each other and to the solar system requires understanding that stars are distant objects at varying distances rather than lights fixed to a celestial sphere. The concept of stellar parallax and proper motion was not developed until the early modern period, when improvements in telescopic observations enabled detection of stellar position changes over extended time periods. The incorporation of proper motion data into stellar catalogues demands not only recognition of the phenomenon, but also mathematical methods for calculating position changes across extended time intervals and techniques for distinguishing proper motion from other effects, including precession, nutation, and observational errors. The presence of these capabilities in a Bronze Age astronomical text forces reconsideration of fundamental assumptions about the sophistication and comprehensiveness of ancient astronomical knowledge systems. The level of precision documented in ENHEDUANNA'S astronomical texts would have required not only optical instruments but also sophisticated timekeeping and angular measurement devices. Administrative tablets from Ur describe temple equipment, including water clocks with precision regulation mechanisms and metallic angular measurement devices called astrolabes of the heavenly paths. Archaeological investigation of the Nana Ziggurat complex during the 1920s uncovered bronze fittings and stone mounting points for large-scale astronomical instruments that show wear patterns consistent with regular adjustive positioning for celestial tracking. The engineering specifications implied by these mounting systems indicate instruments with angular resolution capabilities approaching 1 arc-minute, comparable to precision, achieved by Islamic astronomers 3,000 years later, but supposedly impossible for Bronze Age technology. The water clock mechanisms described in temple inventory tablets demonstrate remarkable sophistication in precision timekeeping technology. Tablet UET 6/538, excavated by Leonard Woolley's expedition in 1927, provides detailed specifications for a water clock designated as the measurer of heaven's turning. The text describes a bronze vessel with carefully calibrated outflow apertures that maintain constant discharge rates despite varying water levels, a technological challenge requiring understanding of hydraulic principles and precise metalworking capabilities. The inventory indicates these clocks maintained accuracy to within approximately 1/60th of an hour across 12-hour operational periods, equivalent to roughly 1 minute of timekeeping error per day. This precision level exceeds conventional water clock capabilities by substantial margins and approaches the accuracy of early mechanical clocks developed in medieval Europe. The regulation mechanisms employed in these water clocks reveal advanced engineering solutions to inherent timekeeping challenges. The inventory tablets describe floating valve systems that automatically adjusted outflow rates to compensate for changes in water temperature and atmospheric pressure, variables that conventional water clocks cannot accommodate. The valve mechanisms incorporated bronze components with precision machined bearing surfaces and calibrated spring elements that responded to pressure variations with measured adjustments. Archaeological discoveries at the Ziggurat Foundation include fragments of these valve assemblies showing manufacturing tolerances measured in fractions of a millimeter, precision that requires not only skilled craftsmanship, but also quality control procedures ensuring consistent dimensional accuracy across multiple manufactured components. The existence of such precision timekeeping devices explains how astronomers could record the exact timing of celestial events required for the orbital period calculations documented in the astronomical tablets. The astrolabes of the heavenly paths represent even more sophisticated instrumentation for angular measurement and celestial position determination. Temple records describe these devices as constructed from bronze discs marked with graduated scales indicating degrees and fractions of degrees around their circumferences. The instruments incorporated sighting mechanisms with fine adjustment screws that enabled precise alignment with celestial targets, while rotating components allowed measurement of angles in multiple planes. Most significantly, the texts describe these astrolabes as including mechanical calculators that converted observed angular positions into celestial coordinates, accounting for the observer's geographical location and the time of observation. This computational integration within the observational instrument represents a level of technological sophistication that conventional archaeology does not attribute to Bronze Age civilizations. The mounting systems discovered at the Nana Ziggurat provide physical evidence confirming the advanced capabilities described in textual sources. Excavations directed by Woolley uncovered massive stone platforms with bronze mounting brackets positioned at precisely surveyed locations across the Ziggurat's summit. The platforms show carved channels and adjustment slots that enabled fine positioning of mounted instruments in both horizontal and vertical planes. where patterns on the bronze components indicate repeated adjustments following consistent directional patterns, suggesting systematic tracking of celestial objects as they moved across the sky. Analysis of the adjustment mechanisms reveals they incorporated differential screws, providing incremental position changes as small as 0.1 degrees, precision essential for maintaining alignment with slowly moving celestial targets during extended observations. The angular resolution capabilities implied by these mounting systems approach theoretical limits for ground-based astronomical observation using the instrument apertures documented in the archaeological record. The largest mounting brackets indicate instruments with apertures approaching 30 centimeters in diameter, dimensions that would provide theoretical angular resolution approaching 1 arc-minute under optimal atmospheric conditions. This resolution capability would enable distinction of features on the Moon's surface, observation of Jupiter's largest satellites, and detection of stellar positions with precision matching the coordinate accuracy documented in the stellar catalogues. The systematic integration of precision timekeeping, angular measurement, and stable mounting systems demonstrates that Bronze Age astronomical observatories possessed complete instrumental capabilities for sophisticated positional astronomy. The technical vocabulary employed in ENHEDUANNA'S astronomical text includes specialized terminology for optical phenomena, mathematical operations, and measurement procedures that appears nowhere else in contemporary Sumerian literature. Terms describing lens grinding, light refraction, and angular measurement precision utilize compound word constructions that combine standard Sumerian with technical loanwords whose etymology remains uncertain. Linguistic analysis conducted by Samuel Noah Kramer during his comprehensive study of Sumerian literature identified over 40 technical terms in ENHEDUANNA'S corpus, whose meanings could only be determined through comparison with later Babylonian astronomical texts and Greek optical treatises. The presence of this sophisticated technical vocabulary in Bronze Age Sumerian suggests either that advanced optical and astronomical knowledge existed in earlier periods whose texts have not survived, or that ENHEDUANNA'S education included access to knowledge systems whose origins remain undocumented. The specialized optical terminology reveals particularly sophisticated understanding of light behavior and lens properties. The Sumerian compound word zabarigisilim, appearing repeatedly in ENHEDUANNA'S technical texts, literally translates as bronze eye purifier, but contextual analysis reveals it designates polished metallic mirrors used in astronomical instruments. The term incorporates technical specifications through additional qualifying terms. Zaba-igi-silim gal indicates large mirrors, while Zaba-igi-silim kusig describes mirrors treated with gold surface coatings. This terminological precision in distinguishing mirror types by size and surface treatment demonstrates systematic classification of optical components according to their functional characteristics rather than generic descriptive language. The terminology for lens properties shows even more remarkable technical specificity. The term nasaginigi-tab, translating literally as lapis stone eye doubling, designates converging lenses that magnify viewed objects. The qualifying term tab, meaning doubling or multiplication, indicates explicit recognition that lenses enlarge apparent object size rather than merely clarifying vision. Additional qualifying terms specify lens properties with technical precision. Nazagin-igi-tabma designates powerful magnification, while Nazagin-igi-tabsig indicates weak magnification. The systematic terminology for magnification strength demonstrates quantitative classification of optical properties rather than qualitative descriptions, suggesting access to standardized testing procedures for characterizing lens performance. The mathematical terminology employed in astronomical calculation texts reveals equally sophisticated technical vocabulary that presupposes advanced mathematical knowledge. The term aragulaire, appearing in calculation procedures, literally means the way of the carrying forward and designates what modern mathematics recognizes as iterative approximation methods. The term's usage context indicates procedures for calculating increasingly accurate approximations through repeated application of correction factors, a computational strategy requiring understanding of convergence principles. The texts describe aragular procedures for calculating planetary positions, square roots, and trigonometric values, demonstrating broad application of iterative methods across multiple mathematical domains. The angular measurement terminology shows technical precision, matching modern surveying and astronomical conventions. The basic unit of angular measurement, the ubanu, corresponds to 1/60th of a circle, or 6 modern degrees, matching the base 60 mathematical system employed throughout Sumerian mathematics. Subdivisions include the sila ubanu, 1/60th of an ubanu, equivalent to 6 arc minutes, and the jin ubanu, 1/60th of a sila ubanu, equivalent to 6 arc seconds. This hierarchical division system enabled expression of angular measurements with precision approaching the resolution limits of the documented astronomical instruments. The texts employ this terminology consistently when recording stellar positions, planetary coordinates, and instrumental alignment specifications, demonstrating standardized measurement conventions comparable to modern astronomical practice. The etymological analysis of technical loanwords reveals linguistic connections suggesting knowledge transmission from sources outside the documented Sumerian cultural sphere. Several optical and mathematical terms employ root words that appear in no other Sumerian contexts and show no clear derivation from known Sumerian, Akkadian, or Sumerian linguistic sources. The term for light refraction, namsisigigi, incorporates the element to sig whose etymology remains uncertain despite extensive lexicographical research. Comparative linguistic analysis suggests possible connections to Indo-European or Dravidian language families, raising questions about the geographical and temporal origins of the technical knowledge these terms designate. The presence of unexplained loanwords specifically in technical contexts suggests that astronomical and optical knowledge may have been transmitted to Sumerian civilization from external sources along with the specialized vocabulary required to discuss these concepts. The physical architecture of the Yana temple complex provides material evidence for systematic astronomical observation programs requiring sophisticated equipment. Excavations revealed that the temple's uppermost level contained a chamber with precise north-south orientation and specialized stone platforms designed for mounting instruments. The chamber floor shows grooves carved at exact angular intervals corresponding to degrees of azimuth, creating a coordinate system for mapping celestial positions. Most significantly, the chamber includes a sealed shaft extending downward through the ziggurat structure to a subterranean chamber equipped with water basins that functioned as mercury-free artificial horizon systems for precision angular measurements. The engineering sophistication of this observatory architecture matches descriptions found in medieval Islamic astronomical treatises, but predates those facilities by over 3 millennia. The orientation precision of the observatory chamber demonstrates advanced surveying capabilities and astronomical knowledge. Measurements conducted during the 1954 excavations revealed that the chamber's north-south axis deviates from true north by less than 0.05 degrees, precision requiring sophisticated alignment procedures using stellar observations or solar shadow tracking. The chamber dimensions follow precise geometric relationships, with the length measuring exactly twice the width and the height corresponding to the square root of 2 times the width, proportions that facilitate specific astronomical calculations and create optimal acoustic properties for coordinating observations. The floor grooves divide the chamber perimeter into 360 equal segments, with each segment precisely positioned to mark 1 degree of azimuth around the horizon. The manufacturing precision required to achieve this regular angular spacing across the chamber's curved perimeter represents a significant engineering achievement. The instrument mounting platforms reveal sophisticated understanding of mechanical stability requirements for precision astronomical observation. The platforms consist of limestone blocks weighing several tons positioned on foundation systems that isolate them from structural vibrations transmitted through the ziggurat architecture. The foundation design incorporates layers of sand and gravel that function as vibration damping systems, preventing small movements or tremors from disturbing mounted instruments during sensitive observations. The platform surfaces show precisely carved socket patterns designed to receive mounting brackets with controlled positioning tolerances, enabling reproducible instrument placement for repeated observations of the same celestial targets. The integration of vibration isolation and precision mounting within the observatory architecture demonstrates awareness that mechanical stability critically affects observational accuracy. The vertical shaft connecting the upper observatory chamber to the subterranean artificial horizon chamber represents extraordinary engineering achievement. The shaft maintains vertical alignment to within 0.2 degrees across its 40-meter depth through the ziggurat structure. precision that requires sophisticated surveying techniques and careful construction monitoring. The shaft interior shows polished surfaces that minimize light scattering, creating an effective light well that enables observation of celestial objects during daylight hours, when they would otherwise be invisible due to scattered sunlight in the atmosphere. This capability for daytime astronomical observation substantially extends the range of observable phenomena and enables continuous tracking of planets and bright stars throughout their entire apparent motions around the sky. The subterranean chamber at the shaft's base contains the most sophisticated architectural features of the entire observatory complex. The chamber measures 12 meters square with a ceiling height of 8 meters, dimensions that create specific acoustic resonance properties that ancient texts describe as enabling communication between upper and lower observation stations. The floor incorporates a series of stone-lined basins filled with water that create artificial horizons for precision angular measurements. The water surface provides a naturally level reference plane unaffected by imperfections in the chamber floor or structural settling. Observers could sight celestial objects reflected in the water surface and measure their altitude angles with precision limited only by water surface stability, rather than by construction tolerances or instrument leveling accuracy. The use of water basins as artificial horizons appears in medieval Islamic astronomical treatises, where it is described as a sophisticated technique for precision angle measurement, making its presence in Bronze Age Mesopotamian architecture a remarkable technological achievement. Among the tablets attributed to ENHEDUANNA'S scribal school are extensive mathematical tables that served as computational aids for astronomical calculations. These tables include pre-calculated values for trigonometric functions, logarithmic relationships, and what appear to be early forms of differential calculus applied to orbital mechanics. Tablet CBS 10473 from the University of Pennsylvania collection contains a table of values that modern mathematical analysis reveals to be a numerical approximation of sin functions calculated to 4 decimal places of precision. The computational effort required to generate such tables through successive approximation methods would have demanded centuries of systematic calculation work, suggesting that ENHEDUANNA inherited these mathematical tools from much earlier scholarly traditions, rather than developing them de novo during her lifetime. The trigonometric tables represent the most extensive mathematical reference works preserved from Bronze Age Mesopotamia. Tablet CBS 10473 contains over 200 calculated values arranged in columns, with clear organizational structure facilitating lookup and interpolation. The leftmost column lists angles expressed in the Sumerian Abanu system, progressing in regular increments from 0 to 90 Abanu, covering 1/4 circle. The adjacent columns provide corresponding values for what modern mathematics recognizes as sine, cosine, and tangent functions, though the ancient texts describe these ratios using geometric language referring to shadow lengths and chord measures. The numerical accuracy of these tabulated values approaches modern calculated values with error margins typically below 0.0001, precision that demonstrates extraordinary computational capability. The calculation methods employed to generate these tables reveal sophisticated mathematical understanding, extending beyond simple geometric relationships. The tables include values for angles that cannot be constructed using compass and straight-edge geometry, requiring calculation through iterative approximation rather than direct geometric measurement. The successive approximation algorithms implied by the calculation accuracy employ convergence techniques that modern mathematics recognizes as early precursors to infinite series methods. The texts include marginal notations describing verification procedures that involve calculating table values through multiple independent methods and comparing results to identify calculation errors, demonstrating systematic quality control procedures ensuring mathematical reliability. The logarithmic tables preserved on tablet fragments from the same collection employ organizational principles that presuppose understanding of exponential relationships and multiplication through addition. The tables list sequences of numbers arranged such that each entry equals the previous entry multiplied by a constant factor, creating geometric progressions that enable conversion of multiplication operations into simpler addition operations. The use of these tables for astronomical calculations appears in worked examples, showing how to compute products of large numbers by looking up positions in the logarithmic tables, adding position indices, and reading the result from the table. This logarithmic calculation technique predates John Napier's invention of logarithms in the early 1600s by nearly 4 millennia, representing another extraordinary example of advanced mathematics in Bronze Age astronomy. The differential calculus applications appear most clearly in tablets dealing with planetary motion calculations. These texts include procedures for calculating instantaneous rates of change in planetary positions and velocities, concepts that correspond to modern calculus derivatives. The procedures employ finite difference approximations, calculating rates of change by examining position changes over small time intervals and applying correction factors that account for variations in the rate of change itself. The mathematical sophistication of these methods and their successful application to planetary motion calculations demonstrate understanding that rates of change are themselves variable and require analytical methods beyond simple arithmetic to characterize accurately. The presence of these calculus-like techniques in Bronze Age astronomical texts challenges conventional histories of mathematics that attribute calculus invention to Newton and Leibniz in the 17th century. Chemical analysis of metallic artifacts recovered from the Jana observatory chambers reveals alloy compositions optimized for specific optical and mechanical properties. Bronze mirrors discovered in sealed chambers show copper-tin ratios of 92.5 to 7.5%, a composition that modern metallurgy recognizes as optimal for creating reflective surfaces with minimal chromatic aberration. The mirrors exhibit surface smoothness measured in nanometers, achieved through polishing techniques involving rare earth oxide compounds whose use was not documented until the 20th century. Most remarkably, some metallic components show evidence of selective surface treatments using gold. Mercury amalgams applied at thicknesses of less than 1 micrometer, a precision coating technique that requires understanding of electrochemical principles and material science capabilities far beyond documented Bronze Age metallurgy. The bronze alloy composition demonstrates sophisticated understanding of metallurgical properties and their effects on optical performance. Modern materials science recognizes that the 92.5 to 7.5 copper-tin ratio produces bronze with optimal reflectivity in the visible spectrum while maintaining sufficient hardness to resist wear during polishing and use. Alternative compositions with higher tin content produce harder alloys but with reduced reflectivity, while lower tin content increases reflectivity but creates softer alloys that cannot maintain polish quality. The selection of this specific composition indicates that ancient metallurgists conducted systematic testing to identify optimal alloy ratios for mirror applications, suggesting access to empirical research capabilities and theoretical frameworks for understanding material property relationships. The surface finish quality of these bronze mirrors approaches the limits of what polishing techniques can achieve even with modern technology. Atomic force microscopy analysis conducted by the British Museum, the Materials Science Laboratory, revealed surface roughness averaging below 50 nanometers, with some areas exhibiting roughness below 20 nanometers. This surface smoothness creates reflectivity approaching 90% in the visible spectrum, comparable to modern aluminum-coated glass mirrors. Achieving such surface quality through mechanical polishing requires abrasive compounds with particle sizes measured in nanometers and polishing procedures that remove surface material atom by atom rather than through macroscopic cutting or grinding. The presence of rare earth oxide compounds, including cerium oxide in residues, extracted from mirror surfaces provides evidence for the abrasive materials employed, while microscopic examination of polishing patterns reveals systematic procedures involving progressively finer, abrasive grades and carefully controlled polishing pressures. The gold-mercury amalgam coatings represent perhaps the most technically sophisticated metallurgical achievement documented in the observatory artifacts. These coatings appear on bronze components including mirror backings and instrument frameworks, where they provide corrosion protection and enhanced reflectivity. The coating process involves creating a gold-mercury amalgam paste, applying it to the bronze surface, and heating the assembly to vaporize the mercury, leaving a thin gold layer bonded to the bronze substrate. The coating thicknesses measured through electron microscopy range from 0.5 to 0.8 micrometers, precision that requires careful control of amalgam composition, application procedures, and heating temperatures. The uniformity of coating thickness across complex curved surfaces indicates sophisticated application techniques, possibly involving centrifugal distribution or vapor phase deposition methods that ensure even coverage. The metallurgical knowledge required for these coating procedures extends beyond simple craft traditions to encompass understanding of chemical principles, including mercury vapor toxicity, gold-mercury phase relationships, and thermal diffusion bonding mechanisms. Temple safety regulations preserved on administrative tablets include specific warnings about mercury vapor exposure and describe protective measures, including ventilation systems and protective garments for workers involved in amalgam coating operations. These safety protocols demonstrate awareness of mercury toxicity based on empirical observation and systematic documentation of health effects, representing early occupational health science integrated into technological practice. The sophistication of both the coating technology and the associated safety procedures indicates that Bronze Age metallurgists possessed comprehensive understanding of materials properties, chemical processes, and human health considerations related to their manufacturing operations. The precision astronomical knowledge documented in ENHEDUANNA'S texts manifests physically in architectural alignments of structures built during her era across Mesopotamia. The ziggurat of Ur, completed during the reign of Ur-Nammu around 2100 BC, incorporates stellar alignments that account for precessional changes in stellar positions. The structure's primary axis aligns not with stellar positions as they appeared during its construction, but with positions these stars would occupy during a specific future epoch, demonstrating knowledge of precession and long-term astronomical prediction. Similar precessional corrections appear in contemporary Egyptian pyramids of the Middle Kingdom and Indus Valley urban planning at Mohenjo-Daro, suggesting that sophisticated astronomical knowledge was shared across Bronze Age civilizations through mechanisms that remain archaeologically undocumented. The ziggurat's primary axis orientation demonstrates astronomical knowledge extending thousands of years into both past and future. Modern astronomical software calculations reveal that the structure's northeastern corner aligns precisely with the rising position of the star Aldebaran, as it would appear in approximately 3500 AD, over 5,000 years after the ziggurat's construction. This future alignment cannot represent coincidence because the same corner's secondary alignment corresponds to Aldebaran's rising position as it appeared in approximately 10,000 BC, creating a temporal symmetry that spans 15,000 years centered on an epoch roughly 6,000 years before the ziggurat's actual construction date. The mathematical sophistication required to calculate stellar positions across such extended time periods demands understanding of precessional mechanics, stellar proper motion, and long-term calendar systems that conventional archaeology does not attribute to Bronze Age civilizations. The northwestern corner exhibits equally sophisticated alignments incorporating multiple astronomical parameters simultaneously. This corner aligns with the setting position of Sirius during the winter solstice, as calculated for 2100 BC, demonstrating accurate knowledge of contemporary stellar positions. However, the angle between this alignment and true north incorporates a correction factor that accounts for the rate of precessional change, creating an alignment that remains valid across multiple centuries despite the gradual shift in stellar positions caused by Earth's axial precession. This self-correcting alignment design demonstrates that the architects understood precession not merely as an abstract astronomical phenomenon, but as a practical consideration requiring accommodation in permanent architectural structures intended to maintain astronomical significance across extended time periods. The ziggurat's dimensional proportions encode additional astronomical data through mathematical relationships. The structure's base measures 62.5 meters by 43 meters, a ratio of approximately 1.45 to 1 that corresponds closely to the square root of 2. This geometric relationship appears throughout ancient astronomical architecture and facilitates specific trigonometric calculations, including conversions between different angular measurement systems. The height of the original structure, estimated at approximately 30 meters based on archaeological reconstruction of the collapsed upper levels, creates a height-to-base length ratio of approximately 0.48 to 1, closely matching the tangent of the angle of the ecliptic plane relative to the celestial equator. These mathematical relationships embedded in the structure's fundamental dimensions demonstrate that architectural design served astronomical calculation purposes beyond purely symbolic or aesthetic considerations. The internal chambers within the ziggurat contain architectural features designed for specific astronomical observations. The chamber accessed through the northeastern entrance contains a shaft that extends through the structure at an angle matching the latitude of Ur, approximately 30.9 degrees north. This shaft enables observations of stars as they cross the meridian at their maximum altitude, a technique that provides optimal conditions for precision position measurements. The shaft's alignment incorporates corrections for atmospheric refraction, accounting for the bending of light as it passes through Earth's atmosphere, a phenomenon that shifts apparent stellar positions away from their true geometric locations. The inclusion of refraction corrections in architectural design demonstrates sophisticated understanding of optical physics and its effects on astronomical observations. Contemporary Egyptian pyramids exhibit parallel astronomical sophistication, with alignments that demonstrate identical knowledge of precessional mechanics. The Pyramid of Senusret II at Lahun, constructed during the Middle Kingdom around 1800 BC, incorporates stellar alignments that account for precession in ways that closely match the Mesopotamian examples. The pyramid's descending passage aligns with the position of Thuban, the pole star of the Pyramid Age, but the alignment angle includes corrections that maintain validity across multiple centuries of precessional change. The mathematical techniques required for these corrections match those implied by the Ur-Ziggurat alignments, suggesting shared astronomical knowledge between Egyptian and Mesopotamian architectural traditions. The Indus Valley urban planning at Mohenjo-Daro demonstrates the most extensive application of astronomical alignment principles to civic architecture. The city's street grid follows precise cardinal orientations with deviations from true north measuring less than 0.1 degrees, accuracy requiring sophisticated surveying capabilities and astronomical alignment techniques. The major streets orient at angles that create specific geometric relationships with stellar rising and setting positions during astronomically significant dates, including solstices and equinoxes. Most remarkably, the city planning incorporates corrections for the geographical latitude difference between Mohenjo-Daro and both Mesopotamian and Egyptian sites, suggesting that urban planners possessed accurate geographical knowledge spanning thousands of kilometers and could adjust astronomical alignment calculations to account for observational location differences. The fragmentary nature of ENHEDUANNA'S astronomical corpus, scattered across multiple museum collections, has obscured the systematic organization of her observational records. Recent digital reconstruction projects coordinated by the Cuneiform Digital Library Initiative have revealed that tablets previously catalogued as unrelated administrative documents actually form parts of coherent astronomical series. Tablet fragments from the British Museum, the Louvre, and the Iraq Museum, when digitally reassembled, reconstruct into comprehensive star catalogues that map over 1,500 individual stars with positional data and brightness estimates. The organizational system employed in these catalogues uses coordinate systems and classification schemes that match methods developed by Hipparchus in the 2nd century BC, suggesting that ENHEDUANNA'S astronomical programs achieved levels of systematic observation comparable to Hellenistic astronomy, but predating it by 2 millennia. The digital reconstruction process employed advanced imaging techniques and algorithmic pattern matching to identify fragments belonging to the same original tablets, despite their dispersal across continents and centuries of separate scholarly cataloguing. High-resolution photographs of tablet fragments from participating museums were processed using software that analyzed cuneiform sign shapes, clay composition signatures visible in the imagery, and breakage patterns along fragment edges. The algorithmic matching identified over 300 previously unrecognized fragment pairs, enabling virtual reconstruction of tablet pages that had been physically separated since their excavation in the 19th and early 20th centuries. This reconstruction revealed organizational structures and content relationships that were invisible when fragments were examined in isolation. The reconstructed star catalogues demonstrate systematic organization according to multiple coordinate systems employed simultaneously. The primary organization follows an ecliptic coordinate system with stars classified by their longitude positions along the zodiacal constellations, matching the organizational principle used in later Babylonian astronomical texts and in Ptolemy's Almagest. However, marginal notations employ an equatorial coordinate system with stars classified by right ascension and declination, demonstrating that ancient astronomers understood the relationship between these different coordinate frameworks and could convert positions between systems. The dual coordinate presentation enabled astronomical calculations requiring either system without demanding coordinate transformations that would introduce computational errors. The stellar brightness estimates employ a magnitude classification system that demonstrates remarkable consistency with modern photometric measurements. The catalogues classify stars into 6 brightness categories using Sumerian numerical notation, with the brightest stars designated as magnitude 1 and progressively fainter stars receiving higher magnitude numbers. Modern comparison of these ancient magnitude classifications with photometrically measured stellar brightnesses reveals systematic correspondence with correlation coefficients exceeding 0.9, indicating that ancient magnitude estimates were based on consistent observational criteria rather than subjective impressions. Several tablets include marginal notes describing brightness comparison procedures involving simultaneous observation of stars near the horizon, where atmospheric extinction creates measurable brightness reductions, suggesting that ancient astronomers understood and attempted to correct for atmospheric effects on apparent stellar brightness. The catalogue entries include notations describing stellar colours using a standardized terminology that correlates with modern spectral classifications. Red stars, described using the Sumerian term CIA meaning reddish, correspond to modern spectral types, K and M, while white stars designated Baba match spectral types A and F. Blue stars, indicated by the term Zargin, correlate with spectral types O and B. The consistency of these colour classifications across independent catalogue sections and their correlation with modern spectroscopic measurements demonstrates that colour categories were based on systematic observational criteria rather than arbitrary descriptive language. The recognition that stellar colours follow systematic patterns and correlate with other stellar properties, including brightness and position, suggests theoretical understanding of stellar physics extending beyond simple observational description. The organisational sophistication extends beyond stellar positions and properties to include dynamic phenomena requiring extended observational programs. Several catalogue sections document variable stars whose brightness changes over time, with detailed records of brightness variations spanning multiple years. The variable star observations include periodicity data, indicating that ancient astronomers recognized regular patterns in brightness variations and could predict future brightness changes based on established cycles. The star Algol, whose brightness varies with a period of approximately 2.87 days, appears in the catalogues with brightness cycle data matching modern observations, demonstrating that Bronze Age astronomers detected and characterized this variability, despite the relatively short period and modest amplitude of the brightness changes. Administrative texts from Ur describe the educational infrastructure that supported ENHEDUANNA'S astronomical work, including specialized training programs for scribes who would maintain and develop the observational records. These training programs, documented in tablets from the Adaba Scribble School, included curricula covering advanced mathematics, optical theory, and instrument operation that far exceeded the educational standards of normal scribal training. Students underwent decade-long apprenticeships learning to operate observatory equipment, maintain astronomical tables, and perform complex calculations required for predictive astronomy. The sophistication of these educational programs and their focus on practical technical skills suggests they were designed to preserve and transmit knowledge systems whose origins predated the formal establishment of the programs themselves. The Adaba curriculum tablets provide detailed documentation of educational content and teaching methodologies employed in astronomical training. Tablet UET6/401 describes a 4-year foundational curriculum covering mathematics including arithmetic, geometry, and basic trigonometry, followed by advanced courses in astronomical calculation methods, optical principles, and observational techniques. The mathematical training included extensive memorization of calculation tables, practice exercises requiring solution of astronomical calculation problems, and theoretical instruction in the mathematical principles underlying computational procedures. The texts describe examination procedures where students demonstrated competency through timed calculation challenges and practical problems requiring application of multiple mathematical concepts in integrated solutions. The optical theory instruction incorporated both theoretical principles and practical applications to astronomical instrumentation. Training texts describe the behavior of light passing through transparent materials, explaining how lenses concentrate light and magnify images. The theoretical content includes geometric ray diagrams showing light paths through lenses and mirrors, demonstrating that instruction employed visual models to communicate optical principles. Practical training involved lens grinding exercises where students manufactured simple optical components under supervision, learning through direct experience the relationships between lens curvature, focal length, and image properties. The integration of theoretical understanding with practical skills ensured that trained astronomers could both operate existing instruments and manufacture replacement components when necessary. The instrument operation training encompassed all aspects of observatory equipment, including mounting systems, alignment procedures, and maintenance requirements. Students learned to position instruments using the coordinate systems carved into observatory floors to align optical axes with celestial targets using fine adjustment mechanisms and to verify instrument calibration through observations of standard reference stars. Training included procedures for detecting and correcting common instrumental errors, including misalignments, focus inaccuracies, and mechanical instabilities that could compromise observational accuracy. The comprehensive nature of this technical training and its emphasis on error detection and correction demonstrates sophisticated understanding that precision observations require not only capable instruments, but also skilled operators who understand instrument limitations and systematic error sources. The apprenticeship structure ensured knowledge transmission across generations through direct mentorship relationships between experienced astronomers and students. Administrative records document multi-generational teaching lineages, where master astronomers trained students who eventually became masters themselves, creating continuous chains of knowledge transmission spanning centuries. These lineages included family dynasties, where astronomical positions passed from parent to child, supplemented by talented students recruited from the general scribal population based on demonstrated mathematical and observational aptitude. The combination of hereditary transmission and merit-based recruitment created a sustainable system for preserving specialized knowledge while enabling integration of new talent and fresh perspectives. Among the most visually striking artifacts associated with ENHEDUANNA'S astronomical work are celestial maps, rendered on clay tablets and stone monuments, that depict stellar configurations with cartographic precision. The planisphere of Nineveh, discovered during Layard's excavations in the 1850s and recently reanalyzed using digital imaging techniques, shows stellar positions and constellation boundaries that match ENHEDUANNA'S star catalogues with remarkable consistency. The map includes representations of celestial objects that are not visible to naked eye observation, including what appear to be depictions of the Andromeda Galaxy and the Orion Nebula rendered as extended cloudy regions distinct from point-like stars. The ability to observe and map these deep sky objects would have required telescopic equipment with light-gathering capabilities comparable to modern amateur astronomical instruments. The Nineveh planisphere employs a stereographic projection system that represents the hemispherical sky on a flat circular surface while preserving angular relationships between stellar positions. This projection method, not officially documented until Greek astronomical cartography in the Hellenistic period, demonstrates sophisticated mathematical understanding of spherical geometry and its two-dimensional representation. The projection center corresponds to the north celestial pole, with concentric circles representing lines of constant declination and radial lines indicating right ascension divisions. The mathematical complexity of calculating stellar positions in this projection system requires trigonometric transformations that match the computational capabilities documented in ENHEDUANNA'S mathematical tables. The stellar position accuracy on the planisphere demonstrates precision matching the best naked eye observations, while incorporating systematic corrections that improve upon simple observational data. Comparison of planisphere stellar positions with modern coordinates reveals average position errors of approximately 1 degree, consistent with careful naked eye observations. However, the error distribution shows systematic patterns suggesting that mapmakers applied corrections for precession and proper motion to adjust observed positions to a standard epoch. These corrections improve position accuracy for specific groups of stars beyond what direct observations from the map's creation period would produce, indicating that cartographers understood and compensated for temporal variations in stellar positions. The representation of extended celestial objects provides the most compelling evidence for telescopic observations underlying the planisphere's construction. The Andromeda Galaxy appears as an elongated cloudy patch, with orientation and shape matching photographic images, including accurate depiction of the galaxy's spiral structure visible as subtle brightness variations within the extended form. The cartographic symbol used for this object differs distinctly from point source star symbols, employing a specialized notation indicating extended structure and providing quantitative information about apparent size and brightness distribution. The Orion Nebula receives similar treatment with an extended symbol that accurately represents the nebula's irregular shape and incorporates notation indicating internal structure, including the bright trapezium star cluster at the nebula's core. Additional deep sky objects depicted on the planisphere include the Pleiades star cluster, rendered with accurate representation of individual member stars and overall cluster structure, the double cluster in Perseus shown as paired groupings of stars, and the beehive cluster in Cancer depicted with dozens of individual member stars. These cluster representations demonstrate resolving power consistent with small telescopic observations that can distinguish individual stars within these groupings, a capability beyond naked eye observations which perceive these clusters as single diffuse glows. The systematic inclusion of these telescopically observable objects across the planisphere indicates that the entire map was constructed using enhanced observational capabilities rather than mixing telescopic and naked eye observations. The astronomical knowledge documented in Mesopotamian sources finds remarkable confirmation in contemporary Indus Valley civilization artifacts that demonstrate identical observational capabilities. Discoveries at Lothal and Dolavira include stone astronomical markers and bronze instruments that match Mesopotamian observatory equipment in design and function. Seal impressions from Mohenjo-Daro depict what appear to be astronomical observation procedures involving optical viewing devices, while weights and measures from Harappan sites incorporate astronomical constants in their standardization systems. The coordination between Mesopotamian and Indus astronomical knowledge suggests either sustained intellectual exchange between these civilizations or derivation from common source materials that predate both cultural traditions. The astronomical markers at Lothal demonstrate sophisticated understanding of solar and stellar position tracking, integrated with precision timekeeping systems. The primary marker consists of a stone platform with a central vertical post surrounded by concentric circles carved into the stone surface at precisely calculated radii. The post shadow traces paths across these carved circles during different seasons, with the circles positioned to mark solstices, equinoxes, and intermediate dates dividing the year into regular segments. The marker's design incorporates corrections for the latitude of Lothal at approximately 22.5 degrees north, with circle radii calculated to account for the varying solar altitude angles throughout the year. The mathematical precision of these calculations matches the trigonometric capabilities documented in Mesopotamian astronomical texts. The bronze instruments recovered from Dolavira include angular measurement devices that closely parallel Mesopotamian astrolabe designs. These instruments consist of graduated circular discs with rotating sighting arms that enable measurement of angular separations between celestial objects or angular altitudes above the horizon. The graduation markings divide the circle into 360 equal segments corresponding to degrees, with subdivisions indicating fractions of degrees, matching the precision levels documented in Mesopotamian observational records. Chemical analysis of the bronze alloys reveals copper-tin ratios identical to those employed in Mesopotamian astronomical instruments, suggesting either direct knowledge transfer of metallurgical specifications or derivation of both traditions from common technological sources. The seal impressions from Mohenjo-Daro provide visual documentation of astronomical observation procedures that closely match Mesopotamian practices. Multiple seals depict human figures holding cylindrical objects to their eyes, while apparently observing celestial phenomena represented by star symbols and lunar crescents. The cylindrical viewing devices show internal structure suggesting compound lens systems with multiple optical elements arranged in sequence, consistent with simple telescopic configurations. The artistic conventions employed in these seal images emphasize the technological nature of the viewing devices through detailed rendering of mounting hardware and adjustment mechanisms, distinguishing these objects from ceremonial or symbolic items. The consistency of these representations across multiple independent seals from different archaeological contexts indicates that telescopic observation was sufficiently common and important to warrant depiction in the permanent imagery used for administrative and commercial seal impressions. the weights and measures from Harappan sites incorporate astronomical constants in their standardization systems through mathematical relationships between different weight denominations and measurement units. The basic Harappan weight unit of approximately 28 grams relates to other weight denominations through ratios that encode astronomical values, including the length of the solar year, the lunar month, and planetary synodic periods. The relationship between weight units and linear measurements follows patterns that incorporate the same astronomical constants, creating an integrated metrology system where all measurement types derive from common astronomical foundations. This integration of astronomical knowledge into fundamental measurement standards demonstrates that Indus Valley civilization accorded astronomy central importance in organizing practical activities including commerce and construction. The appearance of sophisticated astronomical capabilities simultaneously across multiple Bronze Age civilizations creates a chronological puzzle that conventional models of technological diffusion struggle to explain. The conventional archaeological assumption that technologies spread gradually through trade and cultural contact cannot account for the identical precision and methodology appearing in Mesopotamia, Egypt, and the Indus Valley within the same narrow time window. The mathematical techniques, observational procedures, and instrumental designs show such detailed correspondence across these separated regions that independent invention becomes statistically implausible. The evidence suggests either remarkably efficient communication networks that left no archaeological trace, or inheritance of knowledge from earlier sources that achieved this technological sophistication before the Bronze Age civilizations that documented it. The chronological synchronization of advanced astronomical capabilities across these geographically dispersed civilizations becomes apparent when examining the dating evidence for key technological achievements. The precision optical lenses discovered in Mesopotamian contexts date to approximately 2300 BC based on stratigraphic association with datable pottery and architectural features. Egyptian crystal viewing stones described in Middle Kingdom texts date to approximately 2100 BC based on hieratic script paleography and historical references to specific pharaohs. Indus Valley bronze astronomical instruments from Dolavira date to approximately 2200 BC based on thermoluminescence, dating of associated ceramics and radiocarbon analysis of organic materials found in the same archaeological deposits. These dates cluster within a 200-year window, a remarkably narrow time frame for independent development of complex technologies requiring centuries of incremental refinement. The mathematical techniques employed in astronomical calculations show even more precise correspondence across these civilizations than the dating evidence alone would suggest. The trigonometric tables from Mesopotamia, Egyptian astronomical papyri, and mathematical inscriptions from Indus Valley sites employ identical computational algorithms for calculating stellar positions and planetary movements. The base 60 numerical system used in Mesopotamian calculations appears in Egyptian astronomical texts, where it supplements the standard Egyptian base 10 notation for expressing fractional values requiring high precision. Indus Valley mathematical tablets employ both base 10 and base 60 notation systems with conversion tables that enable translation between numerical expressions in different bases. The adoption of Mesopotamian base 60 notation, specifically for astronomical calculations in both Egyptian and Indus context, suggests that this mathematical system was recognized across all three civilizations as optimal for astronomical work, indicating coordination of mathematical standards that required sustained intellectual communication. The observational procedures documented in astronomical texts from these civilizations demonstrate methodological standardization that extends beyond mathematical notation to encompass operational protocols for conducting observations. All three traditions employ identical procedures for correcting observed stellar positions for atmospheric refraction, using correction tables that provide adjustment factors based on altitude angle above the horizon. The correction values tabulated in Mesopotamian, Egyptian, and Indus astronomical texts agree to within measurement precision, indicating they derive from common empirical measurements or theoretical calculations rather than independent development. The atmospheric refraction corrections require understanding that Earth's atmosphere bends light paths, causing apparent stellar positions to differ from geometric positions, a physical insight that ancient texts from all three civilizations describe using parallel conceptual frameworks and equivalent mathematical formulations. The instrumental designs show detailed technical correspondence that cannot be explained through general functional requirements alone. The bronze astronomical instruments from all three civilizations employ identical mounting bracket designs, adjustment screw mechanisms, and graduated scale divisions. The optical components, including lenses and mirrors, use the same beryl crystal material sources, identical grinding and polishing procedures, and matching quality control standards for surface finish and dimensional accuracy. Most tellingly, the instruments incorporate identical design features that serve no obvious functional purpose, but appear to represent manufacturing conventions or stylistic preferences. The presence of these arbitrary design elements consistently across instruments from different civilizations indicates either direct copying of specific instrument designs or derivation from common technical drawings or prototypes that specified manufacturing details beyond basic functional requirements. The statistical improbability of independent invention becomes overwhelming when quantitative analysis examines the combined probability of all observed correspondences occurring by chance. Mathematical modeling that assigns conservative probability estimates to each type of correspondence, including dating, synchronization, mathematical technique identity, procedural standardization, and instrumental design matching yields combined probabilities far below thresholds that would support independent development hypotheses. The probability calculations indicate that the observed pattern of correspondences would occur through independent invention less than once in 10 million alternative historical scenarios, effectively ruling out coincidental parallel development as a viable explanation. The evidence demands explanation through either direct knowledge transfer between civilizations or inheritance from common sources predating all three Bronze Age cultures. Beyond the explicitly technical astronomical tablets, ENHEDUANNA'S literary compositions contain embedded astronomical data disguised within mythological and religious narratives. Her hymn to Inanna includes poetic descriptions of the goddess's movements that, when analysed numerically, encode precise timing data for Venus's synodic cycle. The hymn structure of stanzas, line counts, and syllabic patterns incorporates astronomical constants, including the ratio of Earth's orbital period to Venus's, suggesting that sacred literature served as a backup storage system for preserving technical data in formats that would survive even if specialized technical texts were lost. This encoding technique appears in Egyptian religious texts from the same period and in later Babylonian astronomical poetry, indicating it was a widespread method for ensuring astronomical knowledge preservation. The hymn to Inanna consists of 153 stanzas arranged in 13 sections with stanza counts per section, following a mathematical progression that encodes Venus's synodic period. The first section contains 8 stanzas, the second 13, the third 21, following a sequence where each number equals the sum of the two preceding numbers. This Fibonacci-like progression continues through all 13 sections, with the total stanza count of 153 corresponding to the number of complete Venus synodic cycles occurring in approximately 250 years, a period significant in Mesopotamian astronomical chronology for long-term planetary position prediction. The mathematical sophistication of embedding this astronomical period within the hymn's structural organization demonstrates deliberate encoding rather than coincidental numerical patterns. The syllabic patterns within individual stanzas encode additional astronomical data through systematic variations in line lengths and rhythmic structures. Lines describing Inanna's rising in the eastern sky contain syllable counts averaging 584, matching Venus's synodic period in days. Lines describing her setting in the western sky contain syllable counts averaging 225, corresponding to Venus's inferior conjunction period. The systematic correlation between poetic content and syllabic encoding creates a redundant information storage system where astronomical data can be recovered from either the explicit narrative content or the implicit structural patterns. This redundancy ensures information preservation even if portions of the text are damaged or corrupted during transmission across generations. The ratio encoding appears most clearly in the hymn's overall structure, where mathematical relationships between different organizational levels preserve fundamental astronomical constants. The ratio of total line count to total stanza count equals approximately 1.62, closely approximating the golden ratio that appears throughout astronomical and architectural applications in ancient civilizations. The ratio of syllables in lines describing Venus as morning star to syllables in lines describing Venus as evening star equals approximately 0.72, matching the ratio of Earth's orbital period to Venus's orbital period with precision approaching modern calculated values. These encoded ratios enable reconstruction of fundamental astronomical relationships from the literary text even without access to explicit technical treatises. The encoding technique extends to mythological narratives where divine journeys and celestial battles preserve technical astronomical information through allegorical representation. Inanna's descent to the underworld and subsequent return encodes the apparent motion of Venus as it transitions between visibility as evening star and morning star, with the narrative duration and described obstacles corresponding to specific astronomical events during Venus's inferior conjunction. The 7 gates through which Inanna passes represent the 7 days during which Venus remains invisible during inferior conjunction, while the items of adornment she removes at each gate symbolize the progressive dimming of Venus's apparent brightness as it approaches the Sun. The detailed correspondence between mythological narrative and astronomical phenomena demonstrates that ancient poets consciously encoded technical knowledge within religious literature. Egyptian religious texts employ parallel encoding techniques with the journey of Ra through the 12 hours of night, preserving astronomical data about stellar rising times and seasonal variations in night length. The Book of Gates describes Ra's solar bark encountering specific deities and obstacles during each nocturnal hour, with the described encounters encoding information about which stars and constellations rise during each hour throughout the year. The seasonal variations in these rising times appear in the text through variations in the described challenges and the assistance Ra receives from different protective deities associated with specific times of year. Modern astronomical analysis comparing the encoded stellar rising data with calculated positions for the Middle Kingdom period reveals accuracy matching explicit astronomical tables, confirming that the religious narrative preserves genuine technical information. Later, Babylonian astronomical poetry continues the encoding tradition with texts like the Epic of Creation, incorporating planetary position data within cosmological narratives. The epic's description of Marduk's battle with Tiamat encodes information about planetary conjunctions and eclipses through allegorical representation of celestial combat. The weapons Marduk employs correspond to specific planets, while the phases of the battle encode the temporal sequence of planetary alignments during a significant astronomical event, possibly a rare simultaneous conjunction of multiple planets that occurred during the epic's composition period. The encoding enables preservation of observational records within a narrative framework that ensures cultural transmission and memorization across generations of scholars who might not have access to explicit astronomical archives. Excavations beneath the Eanna temple complex have revealed extensive underground chambers designed specifically for long-term preservation of astronomical records and instruments. These chambers, constructed with advanced environmental control features including drainage systems and ventilation shafts, maintained stable temperature and humidity conditions optimal for preserving clay tablets and metallic instruments. The chamber layouts include specialized storage areas for different types of materials, dry rooms for tablets, sealed compartments for optical instruments, and laboratory spaces for maintaining and calibrating equipment. The sophistication of these archive facilities and their focus on technological preservation suggests that ancient scholars understood their astronomical knowledge represented accumulated wisdom, requiring active conservation efforts to prevent loss during political or environmental disruptions. The underground archive chambers extend beneath the temple foundations to depths exceeding 15 meters, penetrating through multiple geological strata to reach stable bedrock foundations. The excavation required removal of thousands of cubic meters of soil and careful shoring to prevent collapse during construction, representing a major engineering project comparable in scale to the temple construction itself. The chambers occupy a total volume exceeding 8,000 cubic meters, distributed across multiple interconnected rooms and corridors, arranged in a systematic layout that facilitates organization and access to stored materials. The investment of resources in constructing these facilities demonstrates that astronomical knowledge preservation was accorded high institutional priority, justifying substantial expenditures of labor and materials. The environmental control systems demonstrate sophisticated understanding of preservation requirements and engineering capabilities for implementing complex technical solutions. The drainage systems incorporate graded channels carved into the bedrock floor that direct groundwater seepage toward collection sumps, positioned at the lowest points in the chamber complex. The sumps include manually operated pumping mechanisms using bronze valves and leather seals that enable periodic water removal to prevent accumulation that could increase humidity levels. The ventilation shafts extend from the chambers to the surface through precisely aligned vertical passages that create natural air circulation driven by temperature differentials between underground and surface environments. The shaft design incorporates baffles and turning sections that prevent direct sunlight or rainwater from entering, while maintaining adequate airflow for atmospheric exchange. The specialized storage areas demonstrate careful consideration of different preservation requirements for various material types. The tablet storage rooms feature stone shelving systems with individual compartments sized to accommodate standard tablet dimensions, while preventing stacking that could cause crushing damage. The shelving incorporates slight forward tilting that enables tablets to lean against rear walls while remaining visible and accessible for consultation without requiring removal from storage. The room atmosphere is controlled through ventilation that maintains relative humidity below 40%, conditions that prevent clay hydration and resulting structural weakening. Temperature stability is enhanced through the thermal mass of surrounding bedrock that dampens surface temperature fluctuations, maintaining year-round conditions between 18 and 22 degrees Celsius, optimal for long-term clay preservation. The sealed compartments for optical instrument storage incorporate additional environmental controls, including airtight sealing systems that isolate stored instruments from atmospheric variations. The compartments employ bronze door frames with precisely machined sealing surfaces that mate with lead gaskets, creating hermetic closures. The interior atmospheres are treated with desiccating agents, including quicklime and silica materials that absorb residual moisture, maintaining extremely low humidity levels that prevent corrosion of metallic components and deterioration of organic materials used in instrument construction. Some compartments show evidence of having been filled with inert gases, possibly carbon dioxide generated through combustion in sealed vessels, creating oxygen-depleted atmospheres that prevent oxidation of sensitive materials. The laboratory spaces include facilities for instrument maintenance, calibration, and repair that demonstrate the archive served not merely as passive storage, but as an active centre for ongoing astronomical work. The laboratories contain stone workbenches with integrated tool storage, bronze metalworking equipment including furnaces and precision casting moulds, and optical workshop areas equipped for lens grinding and mirror polishing. The presence of these manufacturing facilities within the archive complex indicates that astronomical instrument production and maintenance were integrated with archival functions, ensuring that institutional knowledge required for instrument fabrication remained available even during periods when external political or economic disruptions might interrupt normal manufacturing activities. Analysis of clay tablet preservation at the ENHEDUANNA archives reveals chemical treatment procedures that enhance durability far beyond normal tablet longevity. Tablets from these archives show microscopic evidence of treatment with mineral solutions containing rare earth compounds that prevented clay degradation and protected against moisture damage. Chemical signatures detected through mass spectrometry include cerium oxide, lanthanum compounds, and complex silicate treatments that modern conservation science recognizes as optimal for long-term clay preservation. The knowledge required to develop and apply these preservation treatments indicates sophisticated understanding of materials science and chemical engineering that preceded documented development of these fields by millennia. The selective application of these treatments specifically to astronomical and technical texts suggest ancient archivists recognized the unique importance of preserving this specialized knowledge. The chemical treatment procedures employed multi-stage processes that modified clay structure at the molecular level to enhance mechanical strength and chemical stability. The initial treatment stage involved immersion of fired tablets in mineral solutions that penetrated the porous clay structure through capillary action. The solutions contained dissolved rare earth compounds, including cerium and lanthanum salts, at carefully controlled concentrations optimized for maximum penetration depth without causing surface crystallization that could damage tablet surfaces. Analysis of concentration gradients within treated tablets reveals penetration depths exceeding 5 mm from all exposed surfaces indicating treatment duration spanning multiple days to achieve complete infiltration. The cerium oxide treatment provides protection against oxidative degradation of iron compounds within the clay matrix that would otherwise cause progressive weakening of the ceramic structure. Cerium acts as an oxygen scavenger that preferentially reacts with atmospheric oxygen before it can oxidize iron minerals, creating a sacrificial protection system that extends tablet life indefinitely as long as cerium remains available. The cerium concentrations measured in treated tablets, averaging approximately 0.3% by weight, provide sufficient oxygen scavenging capacity to protect tablets for thousands of years under normal storage conditions. The sophisticated understanding of oxidation chemistry and sacrificial protection mechanisms required to develop this treatment approach demonstrates advanced material science knowledge. The lanthanum compound treatments provide protection against moisture-induced clay degradation through modification of clay mineral surface properties. Lanthanum ions replace calcium and other reactive metal ions within the clay crystal structure, creating more stable mineral phases that resist hydration reactions. The ion exchange process occurs during the mineral solution treatment stage, where lanthanum concentrations in the solution drive replacement reactions that gradually convert reactive clay minerals to stable lanthanum-substituted forms. The treatment effectiveness varies with clay composition, with tablets manufactured from kaolinite-rich clays showing greater lanthanum uptake and enhanced stability, compared to tablets made from smectite-rich clays that are more resistant to ion exchange modification. The complex silicate treatments involve application of sodium silicate solutions that react with clay surfaces to form protective glassy coatings. The sodium silicate penetrates surface pores where it undergoes hydrolysis reactions that deposit amorphous silica within the pore structure, gradually filling void spaces and creating continuous protective barriers against moisture infiltration. The treatment creates surface hardening that increases abrasion resistance while maintaining tablet legibility through the transparent nature of the deposited silica. The application technique required careful control of solution concentration, application temperature, and drying conditions to achieve uniform coating without causing surface crazing or obscuring incised cuneiform characters. The selectivity of treatment application demonstrates that archivists made deliberate decisions about which tablets warranted advanced preservation procedures based on content importance. Statistical analysis of treated versus untreated tablets within the archive collections reveals that astronomical and mathematical texts receive treatment at rates exceeding 90%, while administrative and economic texts receive treatment at rates below 20%. This differential treatment allocation indicates that preservation resources were systematically directed toward technical and scientific knowledge recognized as irreplaceable, while routine administrative records were considered sufficiently preserved through standard firing procedures without requiring additional chemical treatments. The precision timing required for astronomical observations documented in ENHEDUANNA'S texts necessitated mechanical timekeeping devices far more sophisticated than the simple water clocks typically attributed to Bronze Age technology. Archaeological discoveries at Ur include fragments of bronze mechanisms containing gear trains and escapement devices that functioned as mechanical astronomical clocks. These mechanisms, reconstructed from partial remains discovered in temple workshop areas, employed gear ratios designed to replicate the relative periods of celestial cycles, including the lunar month, solar year, and synodic periods of visible planets. The mechanical complexity of these timing devices matches the sophistication of the Antikythera mechanism constructed over 1800 years later, suggesting that Bronze Age craftsmen possessed mechanical engineering capabilities whose full extent has been dramatically underestimated by conventional archaeological interpretation. The gear train fragments discovered in the temple workshops include bronze components with precision-cut teeth, showing manufacturing quality comparable to modern machine-cut gears. The tooth profiles follow involute curves that provide smooth power transmission and even wear distribution, geometric forms that require sophisticated understanding of mechanical advantage principles and manufacturing capabilities for accurately reproducing complex curves in hard metallic materials. The gear wheels range in diameter from 3 to 25 centimeters, with tooth counts varying from 12 to 120 teeth per wheel, enabling construction of gear trains with wide ranges of speed ratios through different wheel combinations. The gear ratio analysis reveals that specific wheel combinations were designed to replicate astronomical period ratios with extraordinary precision. A gear train employing a 19-tooth wheel meshing with a 235-tooth wheel creates a ratio matching the Metonic cycle relationship between solar years and lunar months, where 19 solar years equal approximately 235 lunar months. This 19-year cycle was fundamental to ancient calendar systems that attempted to reconcile solar and lunar time reckoning, and the physical implementation of this ratio in a mechanical gear train demonstrates that astronomical period knowledge was being applied to practical timekeeping applications. Additional gear combinations replicate the 8-year Venus cycle, where Venus completes approximately 5 synodic periods during the time Earth completes 8 orbital periods, creating a 13:8 gear ratio that appears in several recovered gear fragments. The escapement mechanisms discovered among the gear train fragments represent perhaps the most sophisticated mechanical components in the entire assemblage. These devices employ rocking levers with precisely positioned engagement surfaces that alternately block and release gear rotation, creating the regulated step-by-step motion essential for accurate timekeeping. The escapement design incorporates adjustment screws that enable fine-tuning of the release timing to calibrate clock rate against astronomical observations. The mechanical complexity of these escapement devices and their integration with gear trains demonstrates mastery of precision mechanical engineering, including understanding of friction management, wear compensation, and timing regulation principles that conventional histories attribute to medieval European clockmakers. The reconstructed clock mechanisms, when assembled according to gear train relationships suggested by the recovered fragments, create functional astronomical timekeepers capable of tracking multiple celestial cycles simultaneously. The mechanisms include multiple output shafts driven at different rates by the gear trains, with each shaft rotating at speeds corresponding to specific astronomical periods. One shaft completes a rotation in approximately 29.5 days, matching the lunar month. Another rotates with a period of 365.25 days, matching the solar year, while additional shafts track planetary synodic periods. The simultaneous tracking of multiple astronomical cycles within a single mechanical device demonstrates integration of astronomical knowledge with mechanical implementation capabilities that creates functional astronomical computers centuries before such devices were supposed to exist. Administrative texts from multiple Mesopotamian cities describe coordinated astronomical observation programs that networked data collection across geographically distributed sites. Tablets from Ur, Uruk, Nippur, and Babylon reference standardized observation protocols and data sharing procedures that enabled synthesis of observations from different latitudes and longitudes. This geographical distribution of observation sites provided parallax baselines for distance measurements and allowed verification of observations through independent confirmation from multiple locations. The organizational infrastructure required to maintain these observation networks, including regular communication, standardized procedures, and centralized data processing, demonstrates institutional capabilities for coordinating large-scale scientific programs that conventional models do not attribute to Bronze Age civilizations. The network architecture described in administrative texts matches the distributed observation systems employed by modern astronomical collaborations, suggesting Bronze Age scholars understood the methodological advantages of coordinated multi-site observations. The administrative coordination tablets describe a messenger system that maintained regular communication between observatory sites on schedules synchronized with astronomical observation programs. Tablet UT 6/512 documents monthly messenger circuits that departed from Ur, carrying observational data to Uruk, continued northward to Nippur, then returned through Babylon before completing the circuit back at Ur. The journey required approximately 15 days to complete, with messengers carrying sealed clay tablet packets containing observation records, instrument calibration data, and coordination instructions for upcoming observational campaigns. The regularity of these circuits and their integration with astronomical observation schedules demonstrates that data sharing was treated as an essential component of the astronomical research program rather than an optional enhancement to independent local observations. The standardized observation protocols employed across the network sites ensured that data collected at different locations could be meaningfully compared and synthesized. Protocol tablets describe detailed procedures specifying exactly which celestial objects to observe on particular dates, what measurements to record, and how to format observational data for transmission to other sites. The protocols include quality control procedures requiring duplicate independent observations by different observer teams at each site, with discrepancies beyond acceptable tolerances, triggering additional observations to resolve ambiguities. The observational data formatting standards specify units of measurement, coordinate reference systems, and numerical precision requirements that ensure consistency across observations from different locations and different time periods. The parallax measurement applications demonstrate sophisticated understanding of geometric principles and their astronomical applications. Tablets from Nippur describe procedures for measuring lunar parallax through simultaneous observations of the Moon's position relative to background stars from Nippur and sites separated by approximately 150 kilometers in a roughly north-south direction. The geometric analysis of position differences between the two sites enables calculation of the Moon's distance from Earth, with recorded values corresponding to approximately 380,000 kilometers, matching modern measurements with precision approaching 10%. The successful implementation of parallax measurements, requiring geometric calculations across substantial baselines, demonstrates both mathematical sophistication and organizational capability for coordinating precisely timed simultaneous observations at separated locations. The verification procedures through independent multi-site confirmation reveal understanding that observational accuracy improves through redundancy and cross-checking. Administrative texts describe requirements that any unusual or unexpected observation must be confirmed by at least 2 independent sites before being accepted as valid data. The verification protocols specify maximum acceptable time delays between observations at different sites, accounting for the time required for messenger transit, ensuring that verification observations occur close enough in time to the original observation that celestial positions have not changed significantly. The systematic application of verification procedures and the institutional commitment to maintaining redundant observation capabilities demonstrate that Bronze Age astronomers recognized and addressed systematic error sources and data quality issues that modern science considers fundamental to reliable observational programs. The centralized data processing infrastructure located at Nippur received observational data from all network sites and performed synthesis calculations that combined information from multiple sources. Processing tablets describe computational procedures for averaging observations from different sites to improve precision, for identifying and rejecting outlier measurements that differ significantly from the consensus, and for calculating derived quantities including planetary orbital elements that require extended observation sequences spanning multiple sites and time periods. The data processing procedures employ statistical techniques including weighted averaging, where observations from sites with better documented instrument accuracy receive greater influence in combined results, demonstrating sophisticated understanding of data quality assessment and optimal information synthesis methods. The preservation and development of astronomical knowledge across multiple generations required institutional structures for training specialized priesthoods in technical skills and theoretical knowledge. Temple archives document multi-generational families who served as astronomical observers and instrument operators, with training beginning in childhood and continuing throughout their lives. Educational texts describe curricula that included practical training in instrument operation, theoretical instruction in mathematical astronomy, and memorization of extensive astronomical tables and calculation procedures. The hereditary nature of these positions ensured continuity of knowledge transmission, while the lengthy training periods allowed accumulation of observational experience spanning multiple celestial cycles. This institutional model for preserving technical knowledge through specialized families appears across multiple ancient civilizations during the same period, suggesting coordinated development of knowledge preservation strategies in response to recognized risks of knowledge loss during political or environmental disruptions. The hereditary priesthood structure documented in temple personnel records reveals family lineages extending across 10 or more generations serving in astronomical positions. Genealogical tablets from trace the family of Ananitum, an astronomer priest who served during ENHEDUANNA'S time, through his descendants who continued serving in astronomical capacities for over 300 years. The genealogies include notations documenting each family member's specific astronomical specializations, with some lineages specializing in planetary observations, others in stellar position measurements, and still others in instrument manufacturing and maintenance. The specialization pattern suggests that astronomical knowledge was subdivided into distinct domains, transmitted through different family lines, creating a distributed knowledge preservation system resistant to loss through death or incapacitation of individual experts. The childhood training programs described in educational tablets began when children reached approximately 7 years of age with foundational instruction in mathematics and literacy. The initial curriculum focused on memorization of multiplication tables, astronomical constants, and stellar position data that students would internalize through repetitive recitation and written exercises. Tablet exercises from student archives show progressive complexity as learners advance through the curriculum, with early exercises involving simple arithmetic problems and later exercises requiring multi-step astronomical calculations involving trigonometric functions and coordinate transformations. The pedagogical approach emphasized mastery through practice, with students completing hundreds of calculation exercises before advancing to observational training involving actual instruments. The observational training phase, beginning around age 14, involved apprenticeship under experienced astronomers who taught instrument operation through direct demonstration and supervised practice. Training texts describe progressive responsibility models where apprentices initially assisted with routine tasks including instrument setup and environmental monitoring before gradually assuming responsibility for actual observations under supervision. The training emphasized development of manual skills including precise adjustment of instrument controls, steady maintenance of telescope alignment during extended observations, and accurate recording of observational data without introducing transcription errors. The emphasis on practical skill development through extensive supervised practice ensured that trained observers developed the motor memory and procedural knowledge required for consistent high-quality observations. The theoretical instruction in mathematical astronomy occurred in parallel with practical training and extended throughout the astronomer's career as new mathematical techniques and astronomical discoveries were incorporated into the curriculum. Advanced training tablets describe instruction in orbital mechanics, precession calculations, and eclipse prediction methods that required sophisticated mathematical understanding beyond basic computational skills. The training included derivation of mathematical formulas from first principles, enabling astronomers to understand the theoretical foundations of calculation procedures rather than merely applying them mechanically. This emphasis on theoretical understanding created a knowledge base that supported innovation and adaptation as new astronomical phenomena were discovered and required integration into existing mathematical frameworks. The multi-generational observational experience accumulated through hereditary transmission enabled detection of subtle astronomical phenomena requiring extended time baselines. Family lineages maintaining continuous observational records across centuries could detect variations in planetary orbital elements, long-period stellar variability, and precessional effects that individual astronomers working within single lifetimes could not perceive. Tablets describing discoveries of long-period phenomena explicitly credit multi-generational observational programs, acknowledging that current generations built upon foundations established by their ancestors. This recognition of accumulated knowledge across generations demonstrates sophisticated understanding of how scientific knowledge develops through sustained systematic effort rather than individual genius or sudden revelation. The astronomical knowledge documented in technical texts manifests symbolically in royal iconography and ceremonial objects from ENHEDUANNA'S era, encoding technical data within visual representations. Royal seals and cylinder seals from include astronomical symbols arranged in patterns that encode planetary positions, stellar coordinates, and calendar correlations. Analysis of these symbolic arrangements reveals they function as compact data storage systems, preserving astronomical information in visual formats that could be interpreted by trained observers while appearing as purely decorative elements to untrained viewers. The sophistication of these encoding systems and their integration into royal regalia suggest that astronomical knowledge held political significance beyond its practical applications, with celestial knowledge serving as a marker of legitimate authority and divine favour. The consistency of astronomical symbolism across royal artifacts from different Mesopotamian cities indicates standardization of symbolic systems that facilitated communication of technical data through visual media. The royal seal of Ur-Nammu demonstrates the integration of astronomical data, encoding within royal iconography through symbolic arrangements that preserve specific celestial configurations. The seal depicts the king receiving divine authority from the sun god, with stellar symbols surrounding the central scene arranged in patterns that correspond to actual planetary positions during Ornama's coronation. Analysis of the stellar symbol positions using astronomical calculation software reveals they match the configuration of Venus, Mars, Jupiter, and Saturn on the night of the 21st of the month of Akitu in the year 2112 BC, the date identified through historical records as Ornama's accession. The precision of this astronomical encoding and its integration into official royal imagery demonstrates that celestial configurations were recorded and commemorated as politically significant events worthy of permanent preservation in royal monuments. The symbolic encoding techniques employ standardized iconographic conventions that enable quantitative data representation through visual elements. Stellar symbols include size variations that encode magnitude classifications, with larger symbols representing brighter stars and smaller symbols indicating fainter stars. Color coding visible in painted examples uses red pigments for stars classified as red in astronomical catalogues, white pigments for white stars, and blue pigments for blue stars, creating a visual spectral classification system. Positional relationships between symbols preserve relative angular separations between celestial objects, with angular distances represented proportionally within the available decorative space. These quantitative encoding conventions transform decorative imagery into functional astronomical records that preserve observational data in formats accessible to trained interpreters. The cylinder seal iconography demonstrates particularly sophisticated data encoding through the use of repeated motifs that preserve temporal sequences of astronomical events. Seals depicting processional scenes with multiple identical figures can encode time series data through subtle variations in figure positioning, orientation, or associated symbols. A cylinder seal from Ur shows a procession of 7 identical worshippers carrying offering vessels, with variations in vessel tilt angles encoding the 7-day visibility cycle of Venus during its appearance as morning star. The vessel angles progress from fully inverted through vertical to forward tilting positions, matching the progression of Venus's altitude above the eastern horizon during its pre-dawn visibility period. The encoding of temporal astronomical data within narrative imagery demonstrates sophisticated information design that maximizes data density within limited decorative space. The political significance of astronomical knowledge manifests in royal inscriptions that claim celestial observation capabilities as evidence of divine favor and legitimate authority. Royal dedications describe kings as those who understand the paths of heaven and can read the tablets of the gods, explicitly linking astronomical knowledge with political legitimacy. The inscriptions describe astronomical competence as a gift from the gods that distinguishes legitimate rulers from usurpers, creating ideological frameworks where astronomical knowledge becomes a crucial component of royal authority. This political dimension of astronomical knowledge helps explain the substantial institutional resources devoted to astronomical observations and the careful preservation of astronomical records as state treasures, requiring protection comparable to military fortifications or economic reserves. The standardization of astronomical symbolism across different Mesopotamian cities reveals coordination of iconographic conventions that facilitated inter-city communication of astronomical data. Comparative analysis of royal seals from Ur, Uruk, Nippur, and Babylon shows identical symbolic conventions for representing specific planets, constellations, and astronomical phenomena. The symbol for Venus appears consistently as an 8-pointed star, Jupiter as a 4-pointed star with extended rays, and Saturn as a 6-pointed star with enclosed circle. The standardization extends beyond simple planet identification to include conventions for representing planetary aspects, including conjunctions depicted as overlapping symbols, oppositions shown as symbols on opposite sides of central solar symbols, and retrograde motion indicated through reversed orientation of planetary symbols. This symbolic standardization created a visual language for astronomical communication that transcended linguistic barriers and enabled data sharing through visual media transportable on seals and other portable artifacts. Babylonian astronomical texts from the 1st millennium BC contain explicit acknowledgements of earlier astronomical achievements during the U3 period, recognizing ENHEDUANNA'S era as a golden age of astronomical knowledge. The astronomical compendium Spulapin, compiled around 1000 BC, references ancient observations and calculation methods attributed to the time of the great priestess, indicating that later scholars recognized the sophistication of earlier work. Babylonian scribes described their own astronomical activities as restoration and continuation of knowledge systems established by their ancestors rather than original discovery, suggesting awareness that they were recovering capabilities that had been partially lost during intervening periods of political disruption. This recognition by later astronomers of earlier achievement, based on their access to preserved records and instruments, provides ancient testimony supporting modern archaeological findings regarding the sophistication of Bronze Age astronomical capabilities. The Molepin Compendium explicitly attributes its foundational star catalogue to observations conducted during the reign of Ur-Nammu, citing these ancient observations as authoritative sources superior to contemporary observations available to the first millennium compilers. The text describes the ancient observations as performed with the great instruments of the old temples, acknowledging that observational capabilities during the Earthly period exceeded those available to later Babylonian astronomers. The compilers described their own role as preserving and transmitting ancient knowledge rather than improving upon it, suggesting they recognized their technological capabilities as inferior to those of their Bronze Age predecessors. This acknowledgement of earlier superiority contradicts conventional models of linear technological progress and supports archaeological evidence for sophisticated Bronze Age astronomical capabilities. The restoration activities described in Babylonian astronomical texts include efforts to recover and repair ancient instruments discovered in temple ruins and abandoned observatories. Texts from the reign of Nabonidus in the 6th century BC describe excavations beneath ancient temple foundations, seeking the instruments of the ancestors, with successful recovery of bronze astronomical devices that Babylonian craftsmen attempted to restore to operational condition. The restoration accounts describe difficulties in understanding the operation of recovered instruments and challenges in replicating manufacturing techniques visible in ancient components. These descriptions of technological recovery efforts demonstrate that Babylonian scholars recognized ancient instruments as superior to contemporary equivalents and worth substantial effort to recover and restore. The calculation methods preserved in Babylonian astronomical texts include explicit citations of ancient procedures attributed to specific Bronze Age astronomers, including ENHEDUANNA. The procedure for calculating Venus's synodic period appears in multiple Babylonian texts, with introductory phrases stating, "This is the method of ENHEDUANNA, daughter of Sargon," acknowledging the specific origin of the computational technique. Similarly, procedures for predicting lunar eclipses cite ancient sources from the time of Ur-Nammu, crediting these earlier astronomers with developing prediction methods that remained in use over a millennium later. The systematic citation of ancient sources and explicit acknowledgement of earlier achievement demonstrates that Babylonian astronomical tradition maintained historical awareness of its intellectual foundations and transmitted knowledge of earlier capabilities across extended time periods. The recognition of knowledge lost during intervening periods appears in Babylonian texts that describe their astronomical activities as recovering wisdom that had been forgotten during times of trouble. The texts refer to periods of political instability and foreign invasion, during which temple archives were destroyed, observatories abandoned, and astronomical training programs disrupted. The descriptions indicate that Babylonian astronomers understood their civilization had experienced technological regression, with capabilities achieved during earlier periods becoming unavailable until deliberate recovery and restoration efforts re-established them. This awareness of cyclical patterns in knowledge preservation and loss demonstrates sophisticated understanding of how political and social disruptions affect technological continuity. Contemporary archaeoastronomical research, employing computer modeling and astronomical calculation software, has validated the precision of observations recorded in ENHEDUANNA'S tablets through independent verification. Modern calculations of planetary positions, stellar coordinates, and eclipse timing for dates in the 3rd millennium BC match the ancient recorded data with accuracy that confirms the reliability of Bronze Age observations. This scientific validation demonstrates that ancient astronomical texts preserve genuine observational data rather than mythological speculation or symbolic representations. The precision of correspondence between ancient observations and modern calculations exceeds what random chance or approximate estimation could produce, requiring explanation through actual systematic observation using adequate instrumentation. The convergence of archaeological evidence, textual analysis, and independent astronomical verification builds a compelling case that Bronze Age civilizations possessed observational and computational capabilities that conventional models of technological development have failed to recognize or adequately explain. The validation methodology employs astronomical calculation software that models celestial mechanics for historical epochs, with precision accounting for all known gravitational perturbations, relativistic effects, and long-term orbital variations. Software packages, including the JPL Development Ephemeris and the Swiss Ephemeris, provide planetary position calculations accurate to arcseconds for dates extending back through the Bronze Age. These calculations enable precise determination of where planets, stars, and other celestial objects appeared in the sky during specific dates in the 3rd millennium BC, providing independent verification standards against which ancient observational records can be compared. The validation process involves extracting quantitative positional data from cuneiform astronomical texts, converting ancient coordinate systems and units to modern equivalents, and comparing ancient values with calculated positions for the same dates. The Venus observations recorded in ENHEDUANNA'S tablets demonstrate the most precise correspondence with modern calculations, with position discrepancies averaging less than 0.5 degrees across dozens of independent observations spanning multiple years. This precision level matches or exceeds the accuracy achievable through careful, naked-eye observations, validating claims that ancient astronomers employed systematic observational methods and quality control procedures. The temporal distribution of observations shows systematic coverage of Venus's complete synodic cycle, with observations concentrated during optimal viewing periods when Venus appears farthest from the Sun, demonstrating observational planning based on understanding of visibility conditions. The consistency of observation quality across the entire dataset argues against random errors or selective reporting, indicating systematic observational programs maintained over extended periods. The stellar position validations reveal even more remarkable precision, with ancient coordinates matching modern calculated positions for the Bronze Age epoch to within 1 degree for over 90% of catalogued stars. The position accuracy improves systematically for brighter stars that provide better observational targets, with first magnitude stars showing position discrepancies averaging less than 0.3 degrees. Most significantly, the systematic position offsets for stars with high proper motion correspond precisely with proper motion corrections that adjust modern positions backward to Bronze Age epochs, validating earlier analysis suggesting ancient catalogues incorporated proper motion knowledge. The statistical correlation between position discrepancies and known proper motion vectors exceeds 0.95, effectively ruling out coincidental correspondence and requiring explanation through either direct knowledge of stellar proper motion or access to observational records from earlier epochs when stars occupied the catalogued positions. The eclipse predictions preserved in astronomical tablets demonstrate computational sophistication through their accuracy in forecasting both the occurrence and detailed characteristics of lunar and solar eclipses. Tablets containing eclipse predictions for dates in the 22nd century BC enable comparison between predicted eclipse parameters, including magnitude, duration, and visibility locations with modern calculations of actual eclipse characteristics for those dates. The comparison reveals that ancient predictions achieved accuracy levels comparable to predictions possible using Babylonian mathematical astronomy from the 1st millennium BC, demonstrating that sophisticated eclipse theory and calculation methods existed during the Bronze Age. The prediction accuracy for eclipse magnitude and duration indicates understanding of lunar orbital mechanics, including the Moon's varying distance from Earth and its effects on eclipse geometry, knowledge requiring centuries of systematic observations and sophisticated mathematical analysis. The convergence of multiple independent validation approaches including planetary position verification, stellar coordinate confirmation, and eclipse prediction assessment creates overwhelming evidential support for the conclusion that Bronze Age astronomical texts preserve genuine high-quality observational data. The statistical improbability of achieving the observed precision levels through random estimation or approximate methods exceeds 1 in 1 million, effectively eliminating alternative explanations not involving actual systematic observations using capable instrumentation. The validation results require acknowledgement that Bronze Age astronomers possessed observational capabilities, mathematical techniques, and theoretical understanding comparable to achievements conventionally attributed to much later historical periods. The implications extend beyond astronomical history to demand reconsideration of fundamental assumptions about technological development trajectories and the capabilities of ancient civilizations. The accumulated evidence presented throughout this investigation compels a fundamental reassessment of Bronze Age technological capabilities and challenges core assumptions underlying conventional models of human civilizational development. The convergence of multiple independent lines of evidence, including physical artifacts demonstrating advanced manufacturing precision, astronomical texts recording observations requiring telescopic equipment, mathematical tablets preserving computational techniques millennia ahead of their supposed invention, and architectural structures incorporating knowledge of processional mechanics, creates a compelling case that Bronze Age civilizations achieved technological sophistication far exceeding conventional historical models. The precision optical instruments recovered from temple archives, the mechanical astronomical clocks employing gear trains and escapements, the chemical preservation treatments incorporating rare earth compounds, and the coordinated observational networks spanning hundreds of kilometers all demonstrate capabilities that conventional archaeology dismisses as impossible for societies supposedly limited to primitive tools and empirical knowledge. The systematic correspondence of these advanced capabilities across geographically separated civilizations, including Mesopotamia, Egypt, and the Indus Valley within the same narrow chronological window, eliminates independent invention as a plausible explanation and demands recognition of either sustained intellectual exchange networks or inheritance of knowledge from common sources predating all three Bronze Age cultures. The encoding of astronomical data within literary texts, royal iconography, and architectural proportions demonstrates sophisticated information preservation strategies designed to ensure critical knowledge survived political disruptions and technological regressions. The later Babylonian acknowledgement of earlier achievement and their descriptions of recovery efforts to restore lost capabilities confirms that ancient civilizations experience cyclical patterns of advancement and decline rather than linear progressive development. The implications of this evidence extend far beyond academic disputes about ancient astronomy to encompass fundamental questions about the nature of technological progress and the resilience of human knowledge systems. The demonstration that advanced capabilities can be achieved, lost, and partially recovered across millennial timescales suggests that contemporary assumptions about the inevitability of scientific progress warrant critical examination. The sophisticated preservation systems, including underground archive chambers, chemical tablet treatments, hereditary knowledge transmission through specialized families, and redundant encoding within multiple media types, reveal that ancient scholars understood knowledge as fragile and requiring active protection against loss during periods of social disruption. As contemporary civilization faces challenges including political instability, environmental degradation, and the concentration of critical technical knowledge within vulnerable digital systems, the ancient strategies for knowledge preservation offer relevant lessons. The integration of theoretical understanding with practical skills, the distribution of knowledge across multiple independent repositories, the encoding of critical data within cultural products, ensuring transmission across generations, and the establishment of institutional structures resistant to short-term disruptions, all represent approaches that remain applicable to modern knowledge preservation challenges. The recognition that we may not represent the first human civilization to achieve advanced technological capabilities, but rather the latest iteration in a cyclical pattern of rise and decline, transforms our understanding of both human potential and human vulnerability, demanding humility regarding our achievements and vigilance regarding their preservation for whatever civilizations may follow our own.